Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the outer reaches of our solar system, where sunlight barely penetrates the cosmic darkness, orbits one of the most intriguing worlds humanity has ever discovered. Titan, Saturn's largest moon, presents a landscape so alien, yet eerily familiar, that it has revolutionized our understanding of where life might emerge in the universe. At negative 179 degrees Celsius, Titan's surface temperature would instantly freeze any Earth-based organism solid. Yet this frigid world harbors something extraordinary. Vast lakes and seas filled not with water, but with liquid methane and ethane. These hydrocarbon bodies stretch across hundreds of kilometers, creating the only stable surface liquids known to exist anywhere in our solar system beyond Earth. The Cassini-Huygens mission, which concluded its 13-year exploration of the Saturn system in 2017, revealed Titan to be a world of startling complexity. Radar observations pierced through the moon's thick orange atmosphere to map coastlines, river channels, and vast polar seas. The largest of these, Kraken Mare, spans roughly 400,000 square kilometers, larger than the Caspian Sea on Earth. What makes Titan truly remarkable is its methane cycle, a process that mirrors Earth's water cycle in stunning detail. Methane evaporates from the surface seas, rises through the atmosphere, condenses into clouds, and falls as rain. This precipitation carves river valleys, fills lakes, and reshapes the landscape through processes of erosion and deposition that would be instantly recognizable to any Earth geologist. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The Huygens probe, which successfully landed on Titan's surface in January 2005, provided our first ground truth observations of this alien world. Its instruments detected a complex organic chemistry occurring in the atmosphere, where ultraviolet radiation from the distant sun breaks apart methane molecules, creating a cascade of chemical reactions that produce dozens of organic compounds. These organic molecules rain down onto Titan's surface like a continuous shower of chemical building blocks. Over billions of years, this process has deposited what scientists estimate to be hundreds of times more organic material than all of Earth's coal, oil, and gas reserves combined. This organic inventory represents one of the largest reservoirs of complex carbon chemistry known in the solar system. But perhaps most intriguing is what lies beneath Titan's icy crust. Gravitational measurements from Cassini revealed that Titan harbors a subsurface ocean of liquid water, likely containing more water than all of Earth's oceans combined. This hidden ocean, sandwiched between layers of ice and rock, may maintain liquid conditions through tidal heating generated by Saturn's immense gravitational pull. The coexistence of surface hydrocarbon seas and a subsurface water ocean creates a unique dual environment that has captured the imagination of astrobiologists worldwide. While life as we know it requires liquid water, the possibility of alternative biochemistries based on hydrocarbon solvents opens entirely new avenues for biological speculation. Titan's atmosphere, composed primarily of nitrogen, with a small percentage of methane, maintains surface pressures 50% higher than Earth's. This thick atmospheric blanket, combined with the greenhouse effect of methane, keeps the surface temperatures stable enough to maintain liquid hydrocarbons, a crucial requirement for any potential hydrocarbon-based life. As we stand on the threshold of a new era of Titan exploration, with NASA's Dragonfly mission scheduled to launch in 2027, we find ourselves confronting fundamental questions about the nature of life itself. Could biochemistry function in liquid methane? Might microbial communities thrive in the depths of Kraken Mare? The answers may reshape our understanding of biology and our place in the cosmic community. The atmosphere of Titan functions as a vast chemical laboratory, continuously synthesizing organic molecules through processes that have operated for billions of years. When ultraviolet photons from the sun strike methane molecules in Titan's upper atmosphere, they trigger a complex cascade of photochemical reactions that produce an astonishing variety of carbon-based compounds. This photochemical factory begins with the simplest hydrocarbon, methane, which consists of one carbon atom bonded to 4 hydrogen atoms. When high-energy photons break these bonds, the resulting fragments recombine in countless ways, forming progressively larger and more complex molecules. Ethane, propane, acetylene, and benzene all emerge from this atmospheric chemistry, along with nitrogen-bearing compounds called nitriles. The process doesn't stop with simple hydrocarbons. As these molecules continue to react and grow, they form increasingly complex structures, including polycyclic aromatic hydrocarbons, or PAHs, which contain multiple carbon rings. Some of these compounds reach such complexity that they begin to aggregate into tiny particles, creating the haze that shrouds Titan's surface and gives the Moon its characteristic orange appearance. What makes this chemistry particularly fascinating is its potential relevance to the origins of life. Many of the organic compounds raining down on Titan's surface are identical to those found in meteorites and comets, the same materials that may have delivered the building blocks of life to early Earth 4 billion years ago. In essence, Titan provides a natural laboratory for studying prebiotic chemistry on a planetary scale. But the real question that drives astrobiological speculation is whether life could function directly in Titan's hydrocarbon environment. Traditional Earth-based biochemistry relies on water as a solvent because of its unique properties. Water dissolves many organic molecules, facilitates chemical reactions, and remains liquid across a temperature range compatible with complex chemistry. Liquid methane and ethane possess very different solvent properties. They dissolve different types of molecules than water, potentially enabling entirely different kinds of biochemical reactions. While water-based life relies heavily on polar molecules that dissolve easily in water, methane-based life might depend on non-polar molecules that dissolve readily in hydrocarbon solvents. Cornell University's chemical engineer Paulette Clancy has spent years exploring this possibility through computer simulations. Her work suggests that large complex molecules called azotosomes could function as cell membranes in liquid methane. These structures, composed of nitrogen, carbon, and hydrogen, could potentially encapsulate chemical reactions and maintain the organization necessary for life. The energy sources available on Titan present both challenges and opportunities for hypothetical life forms. Solar energy is scarce, with sunlight approximately 100 times dimmer than on Earth. However, chemical energy abounds in the form of organic molecules continuously produced in the atmosphere. Any methane-based organisms might function as living hydrocarbon engines, using the chemical energy stored in complex organic compounds. Research by astrobiologist Christopher McKay suggests that methane-based life might consume atmospheric acetylene and hydrogen, producing methane as a waste product. Intriguingly, Cassini observations revealed lower than expected concentrations of acetylene and hydrogen at Titan's surface, though multiple non-biological explanations could account for these observations. The temperature constraints on Titan create additional biochemical challenges. At -179 degrees Celsius, all chemical reactions proceed much more slowly than at Earth temperatures. Any hypothetical Titanian life would need to operate on vastly different timescales, with metabolic processes potentially requiring thousands of years to complete cycles that take seconds in terrestrial organisms. Despite these challenges, the sheer abundance of organic chemistry on Titan provides an enormous reservoir of potential building blocks. The Moon's surface contains an estimated inventory of organic compounds equivalent to several hundred times Earth's total fossil fuel reserves. This represents an almost unimaginable abundance of chemical raw materials for any processes, biological or otherwise, that might utilize hydrocarbon chemistry. As our understanding of Titan's chemistry deepens, we begin to appreciate the Moon as more than just a curiosity in our solar system. It represents a natural experiment in organic chemistry that has been running for billions of years, potentially offering insights into alternative pathways for the emergence of complexity and, perhaps, life itself. The lakes and seas of Titan represent one of the most extraordinary discoveries in planetary science, revealing a world where familiar geological processes operate under completely alien conditions. Through 13 years of radar observations, the Cassini spacecraft mapped these hydrocarbon bodies with remarkable precision, uncovering a complex hydrological system that rivals Earth's in its sophistication. Titan's largest sea, Kraken Mare, dominates the Moon's northern polar region, with an area exceeding 400,000 square kilometers. This vast body of liquid methane and ethane stretches nearly 1,200 kilometers at its longest point, with depths potentially reaching several hundred meters. Along its irregular coastlines, radar images reveal features that would be instantly familiar to any Earth oceanographer: bays, straits, islands, and what appear to be river deltas where hydrocarbon streams empty into the main body. Ligeia Mare, the second largest sea, covers approximately 126,000 square kilometers and displays remarkably smooth radar properties, suggesting a composition dominated by liquid methane with minimal dissolved solids. Spectroscopic observations from Cassini revealed that Ligeia Mare's surface reflects radar signals in a manner consistent with pure liquid hydrocarbons, indicating remarkably uniform composition across its entire extent. The smaller Punga Mare completes the trio of major northern seas. Though dozens of smaller lakes dot the polar landscape, these smaller bodies show greater compositional variety, with some displaying radar properties suggesting higher concentrations of dissolved organic compounds or suspended particles. The variation in radar brightness across different lakes provides crucial clues about their individual chemical compositions and evolutionary histories. What makes Titan's hydrocarbon seas particularly intriguing is their dynamic behavior. Unlike the static bodies of liquid one might expect on such a cold world, these seas show clear evidence of seasonal changes driven by Titan's orbital mechanics. A Titan year lasts 29.5 Earth years, creating seasons that span over 7 Earth years each. During Titan's northern winter, which lasted from 1995 to 2009, the northern seas grew larger and deeper as methane precipitation concentrated in the polar regions. Cassini observed the appearance of new temporary lakes and the expansion of existing bodies as the seasonal methane cycle redistributed liquid across the Moon's surface. The southern hemisphere tells a different story. While the north hosts the Great Permanent Seas, the south contains primarily dry lake beds called lacunae. These empty basins, identified by their distinctive radar signatures, suggest that liquid hydrocarbon bodies migrate between hemispheres following the seasonal cycle. Much like Earth's monsoon patterns redistribute water between different regions. Perhaps most remarkably, Cassini detected what appear to be waves on the surfaces of Titan's seas. Initial observations showed mirror-smooth surfaces that reflected radar signals like perfect mirrors. However, later observations revealed slight roughening of the surface, suggesting the development of small waves possibly driven by wind or tidal forces. The discovery of these surface waves carries profound implications for understanding Titan's atmospheric dynamics. The generation of waves requires wind speeds of at least 1 meter per second, indicating more active atmospheric circulation than previously suspected. These observations suggest that Titan's thick atmosphere can transfer enough energy to its surface to generate wave action, creating dynamic interfaces between liquid and gas. Temperature measurements of the hydrocarbon seas reveal another layer of complexity. Different areas within the same sea show slight temperature variations, suggesting mixing processes that distribute heat unevenly. These temperature differences, though small, indicate active circulation within the liquid bodies, currents and convection patterns that transport material and energy across the seascapes. The chemical composition of individual seas shows intriguing variations. While all contain primarily liquid methane and ethane, the relative proportions differ significantly between bodies. Some lakes appear methane-rich, while others show elevated ethane concentrations. These compositional differences likely reflect local variations in evaporation rates, seasonal cycles, and the input of fresh organic material from atmospheric precipitation. Shore morphology around Titan's seas provides additional insights into their behavior over geological time. Some coastlines show sharp, well-defined edges, suggesting recent liquid levels, while others display terraced structures indicating historical high water marks. These features suggest that Titan's seas have varied significantly in size and depth over longer timescales, possibly responding to climate cycles or changes in atmospheric composition. The detection of dissolved nitrogen in some hydrocarbon bodies adds another dimension to their chemistry. Nitrogen solubility in liquid methane increases with pressure, meaning that deeper portions of the seas likely contain higher concentrations of dissolved nitrogen, a potential energy source for any hypothetical methane-based organisms that might inhabit these alien waters. Beneath Titan's hydrocarbon seas and organic-rich surface lies one of the solar system's most intriguing secrets, a vast ocean of liquid water that may contain more H2O than all of Earth's oceans combined. This hidden ocean, detected through careful analysis of Titan's gravitational field and shape changes, represents a completely separate aquatic environment from the surface methane seas, one that might harbor life as we know it. The discovery of Titan's subsurface ocean emerged from precise measurements of the Moon's gravitational field conducted by Cassini during multiple flybys. As the spacecraft passed close to Titan, tiny variations in its radio signal revealed how the Moon's mass was distributed internally. These measurements indicated that Titan's interior contains a layer of material less dense than rock, but denser than ice, strongly suggesting a substantial body of liquid water. Additional evidence came from observations of Titan's shape as it orbits Saturn. Tidal forces from Saturn's immense gravity should cause Titan to deform slightly as it follows its elliptical orbit. The magnitude of this deformation depends critically on the Moon's internal structure. The observed tidal response matches theoretical predictions for a Moon containing a global subsurface ocean approximately 50 to 200 kilometers thick. This subsurface ocean likely exists between 50 and 100 kilometers beneath Titan's surface, sandwiched between an outer shell of water ice and an inner core of rock and metal. The ocean's temperature, maintained by tidal heating and possibly radioactive decay in Titan's rocky core, probably ranges from 0 to 4 degrees Celsius, well within the range that supports liquid water. The chemical composition of Titan's subsurface ocean remains largely unknown, but theoretical models suggest it likely contains dissolved salts and possibly dissolved organic compounds that have migrated downward from the surface over geological time. The ocean might also harbor dissolved gases from Titan's interior, including hydrogen sulfide, ammonia, and carbon dioxide, compounds that could serve as energy sources for chemosynthetic organisms. What makes Titan's subsurface ocean particularly intriguing from an astrobiological perspective is its potential longevity. While surface conditions on many worlds change dramatically over geological time, subsurface oceans can remain stable for billions of years. If life emerged in Titan's hidden ocean, it might have had ample time to evolve into complex forms. Therefore, energy sources available in Titan's subsurface ocean could support various forms of life. Hydrothermal activity at the ocean floor, driven by tidal heating and radioactive decay, might create chemical gradients similar to those that support thriving ecosystems around Earth's deep-sea hydrothermal vents. These environments could sustain chemosynthetic organisms that derive energy from chemical reactions rather than sunlight. Perhaps most intriguingly, Titan's subsurface ocean might not exist in complete isolation from the surface hydrocarbon system. Theoretical models suggest that material exchange could occur between the two liquid realms through various mechanisms. Impact craters could occasionally breach the ice shell, allowing temporary communication between surface and subsurface environments. Cryovolcanic activity represents another potential pathway for material exchange. Several features on Titan's surface show characteristics consistent with ice volcanism, where liquid water and dissolved materials erupt through the ice shell to reach the surface. These eruptions could transport subsurface ocean material, including any microbial life, to the surface environment. The possibility of life existing simultaneously in both of Titan's liquid environments opens fascinating questions about biological exchange and adaptation. Could organisms originating in the water ocean adapt to survive in hydrocarbon seas? Might genetic material transfer between these radically different environments, creating hybrid biochemistries that utilize both water-based and hydrocarbon-based chemistry? Recent theoretical work by astrobiologist Shannon Mackenzie suggests that the boundary between Titan's ice shell and subsurface ocean might harbor particularly interesting chemistry. This interface region could concentrate organic compounds, migrating downward from the surface, while also receiving energy from hydrothermal processes below. Such boundary zones often prove to be hotspots for biological activity on Earth. The depth and pressure of Titan's subsurface ocean create conditions unlike anything in Earth's surface biosphere, but similar to the deep ocean environments that harbor some of our planet's most extremophile organisms. High-pressure, low-temperature conditions might favor the formation of complex organic molecules and support metabolic processes that operate slowly but efficiently. Isotopic analysis of Titan's atmosphere provides additional clues about the subsurface ocean's composition. The ratios of different nitrogen isotopes suggest that Titan's atmosphere has been in contact with liquid water at some point in the Moon's history, possibly indicating episodic communication between the subsurface ocean and surface environment. Understanding the dynamics of Titan's dual liquid systems requires considering how they might influence each other over geological time. Changes in surface pressure, caused by seasonal cycles or long-term climate evolution, could affect the depth and extent of the subsurface ocean. Similarly, changes in tidal heating or internal structure could influence how much liquid water remains accessible beneath the ice shell. The next chapter in Titan exploration promises to revolutionize our understanding of this enigmatic world and its potential for harboring life. NASA's Dragonfly mission, scheduled to launch in 2027 and arrive at Titan in 2034, represents the most ambitious attempt yet to explore the surface of Saturn's largest moon in unprecedented detail. Dragonfly breaks new ground as the first mission to employ a nuclear-powered rotorcraft for planetary exploration. This 8-rotor drone will possess the ability to fly across Titan's landscape, covering distances that would be impossible for traditional landers. The thick atmosphere and low gravity, 14% of Earth's, create ideal conditions for powered flight, allowing Dragonfly to hop between scientifically interesting locations across hundreds of kilometers. The mission's primary landing site, Shangri-La, represents a vast equatorial region covered in organic dunes that stretch for hundreds of kilometers. These linear dunes, composed of complex organic particles that have precipitated from Titan's atmosphere over millions of years, contain the accumulated products of Titan's atmospheric chemistry. By analyzing these materials, Dragonfly will essentially sample billions of years of organic chemical evolution. Dragonfly's scientific payload includes a drill system capable of extracting subsurface samples for detailed chemical analysis. The BEAN mission will search for biosignatures, chemical indicators that might reveal whether life has emerged in either of Titan's liquid environments. These might include unusual isotopic ratios, complex organic molecules organized in ways that suggest biological processes, or chemical gradients that indicate active metabolism. The rotorcraft's mobility will enable it to investigate multiple environments during its planned 2-year mission. Beyond the organic dunes, Dragonfly will explore crater rims where impact events may have excavated material from Titan's subsurface, potentially providing access to samples from the hidden water ocean. The mission may also investigate areas where cryovolcanic activity has brought subsurface materials to the surface. Advanced spectroscopy instruments aboard Dragonfly will analyze the composition of Titan's atmosphere, surface materials, and any liquids encountered during the mission. These measurements will provide unprecedented detail about the chemical processes operating on Titan and help determine whether any of the observed chemistry shows signs of biological influence. Looking beyond Dragonfly, several proposed missions could further advance Titan exploration. The Titan submersible concept envisions a nuclear-powered submarine capable of diving beneath the surface of Kraken Mare to explore the depths of Titan's hydrocarbon seas. Such a mission could directly sample the seafloor, investigate any sedimentary deposits, and search for signs of biological activity in the liquid methane environment. The European Space Agency has proposed the Titan Lake In Situ Sampling Propelled Explorer, or TLISPE, which would deploy a floating probe on one of Titan's northern seas. This mission would study sea composition, search for organic compounds dissolved in the hydrocarbon liquids, and monitor seasonal changes in the sea's chemistry and behavior. Perhaps most ambitiously, future missions might attempt to access Titan's subsurface ocean directly. Cryobot technology, currently under development for exploring Europa's subsurface ocean, could potentially be adapted for Titan. A nuclear-powered probe could melt through Titan's ice shell to reach the hidden water ocean, where it would deploy sensors to search for signs of life in this alien aquatic environment. The technological challenges of Titan exploration remain formidable. The extreme cold requires all instruments and mechanical systems to function at temperatures that would freeze most materials solid. Power generation in the dim sunlight requires nuclear sources, adding complexity and regulatory challenges to mission planning. Communication delays of over an hour each way make real-time control impossible, requiring autonomous navigation and decision-making capabilities. Despite these challenges, the scientific potential of Titan exploration justifies the investment. Discovery of life in Titan's seas, whether hydrocarbon-based organisms in the surface lakes or familiar biochemistry in the subsurface ocean, would represent one of the most significant discoveries in the history of science. Such a finding would demonstrate that life can emerge under conditions radically different from those on Earth, greatly expanding the potential for biology throughout the universe. Even if no life exists on Titan, the Moon's complex organic chemistry provides invaluable insights into the processes that may have led to life's emergence on Earth. The organic compounds raining down on Titan's surface include many of the same molecules found in meteorites and comets, the materials that may have delivered life's building blocks to the early Earth 4 billion years ago. As we stand at the threshold of this new era of Titan exploration, we find ourselves confronting fundamental questions about the nature of life, chemistry, and planetary evolution. The answers await in the methane seas and hidden oceans of Saturn's most mysterious moon, where the next chapter of astrobiology will be written in the language of hydrocarbon chemistry and the eternal dance between liquid and life.